Hello, here we're going to continue our look at probability and start to look at probability of multiple events. So there's two types of events. There's dependent events and independent events. So dependent events are when one outcome impacts the next. And we'll see some examples down below. Independent events are when one event or one outcome does not impact the other. And so we're going to go through and decide if the following are dependent or independent events. So example 1, rolling a dice and then spinning a spinner. These are independent because whatever happens on that dice, it has no bearing on the spinner. They're totally separate. Rolling the dice, no matter how you do it, whatever, will not impact spinning the spinner. Picking a piece of candy from a bag, then picking another piece of candy. These are dependent. Because, say there's 30 pieces of candy in there, when you pull a piece of candy out, now there's only 29 pieces of candy in there. So the odds of the second one have changed because the denominator has changed. So these are called dependent events. Same thing with cards. If we're drawing an 8 and then we're trying to draw a 7, those are dependent because once we take the 8, the probability of drawing a 7 changes because there's one less card. Now, if we draw an 8, put it back, then we try to draw a 7, and I'm assuming we shuffle in between there, that would be independent. Because once you put that 8 back and reshuffle, the odds are just the same for drawing the 7 as they would have been for drawing the 8 because the deck's back to its original state. If two events are independent, then the probability of A and B, so both occurring, is you're going to find the probabilities of them separately and multiply them together. So let's take a look here. At a picnic, there are 10 diet drinks and 5 regular drinks. There are 8 bags of fat-free chips and 12 bags of regular chips. If you're randomly given a drink and a chip, what's the probability that you get a diet drink and normal chips? So what we do is that there's 10 out of 15 diet drinks, right? Because there's 15 total drinks. So that's the probability that we would get a diet drink. And if we want to also figure out what's the probability we got the right drink and the right bag of chips, which would be 8 over 20. If I multiply those together, and yes, you can simplify them too. So we could call this really 2/3 times 2/5 to get 4 over 15. And when we turn that into a percent, there's a 26.6% chance that both of those things would happen. That you would get the diet drink you want and the bag of chips that you want. So we had some independent events up here. Say you were trying to roll on this dice. Say you wanted to roll a 5. So 1/6 chance of that. And then say the spinner had 4 slots on it. And you wanted to get one of the specific slots. So if you were trying to guess what the dice was going to land on and what the spinner was going to land on, and for both of those to happen, you only have a 1 out of 24 chance of that happening. So for a deck, if you plan on drawing an 8, there's 4 8s in there out of 52 total cards. And then if we put it back and try to draw a 7, it's another 4 out of 52 chance. And if you multiply those together, it's very small. You have a point, I'll round it up, let's go 0.59% chance of, if you have a deck of cards, drawing an 8, reshuffling, and then drawing a 7. And that should make sense because there's a ton of possibilities that could come about. So whenever we're multiplying probabilities together, it gets less and less likely. Let's take a look at one that's going to be very unlikely. Given a true or false test with 7 questions, what's the probability of guessing every answer correct? Well, you have a 50% chance, right? And you'd be multiplying that 50% chance over and over again, all 7 times. So really, this is 1/2 to the 7th power. You know, from our rules of exponents, it's really just 1 over 2 to the 7th power. 2 to the 7th power is 1 out of 128 here. So your probability of guessing all of them correct would be 0.78%. So what this fraction is really saying is if I gave a 7 true or false test and out to all my students, I usually have somewhere around 128 students, and everyone just had to guess, we'd expect one person out of all 128 to guess all 7 questions correct. So that's when you're multiplying 2 independent events together. So all other probability is going to be addition if they are not independent events. There's 2 formulas that we're going to be looking at here. So if we're looking at 2 things and we want either one, so A or B, what we're going to do is do the probability of A plus the probability of B, and then right here, the probability of A and B happening at the same time. And so that's going to seem confusing at first. Once we come down here to this circle and triangle and square shapes, it'll start to make more sense. This is the formula that we'll use when things can happen in multiple ways. However, there's also a scenario where 2 events cannot happen at the same time, and they're called mutually exclusive. And if 2 events are mutually exclusive, then the probability is simply just adding them up together. So let's take a look at an example of mutually exclusive and an example of a non-mutually exclusive event. An example of mutually exclusive, which would be this formula right here, would be this. Let's say it's one of the limited menu item days in the lunchroom, and to where you can either get pizza or you can get a deli sub. All right, let's say those are 2 of the options. Those are mutually exclusive because if you're only getting one meal, you can only get one or the other. An example of a non-mutually exclusive event would be something like this. Say it's the week of Buff Chick Pizza. Alright, and what we want to figure out is what's the probability of someone getting pizza or the probability of someone getting something that has buffalo in it. Right? And so the reason that this is going to be non-mutually exclusive is because there is a pizza option that has buffalo on it. So what we're going to have to do is a little more work to where we'll add up some of the percentages, but then we'll also need to take away where both of them are existing at the same time. And so what we're going to do is we're going to see some examples with some actual numbers to get used to mutually exclusive and non-mutually exclusive. So let's look at the first example, which is going to be mutually exclusive. So a school requires you to take 1 foreign language a year, French or Spanish. 37% of students take French and 15% take Spanish. What's the probability of you sitting next to a French or Spanish student at lunch? Well, you can't take both French and Spanish, so all we'd have to do here, since these are mutually exclusive, is add up the probabilities together. And when we do this, so the probability of someone taking Spanish or French is simply adding up those together. And when we do that, we would get an answer of 0.52, which is 52%. So those are much more easier. Mutually exclusive are much more easy because all we have to do is add the 2% together. So let's look at one that's now going to be non-mutually exclusive. So what's the probability of you picking a round or green shape off of this plate? So we want the probability of a round or green shape. So here's what we're going to have to do. We're going to first need to find the probability of round. So when we look at it, here's a round, here's a round. So we have 1, 2, 3, 4, 5 round out of a total of 9 shapes. So that's the probability of getting a round shape. Now we're going to add it with the probability of green. And you can see that there's 3 green out of 9. But here's the issue. These aren't mutually exclusive. What that means is that there's a way to have something that's both round and green, and that's where this subtraction part comes in. Whenever you're looking for these odds, so if we're looking for a round or green, we're going to need to subtract the probability that something is round and green in order to make this all sort out. So when we go to do that and we look, there are 2 shapes that are both round and green. And so then now we would be able to get all these to go together. And when we do that, we'd end up getting 6 out of 9. So we get 2/3 or 66.6% chance of getting something that is round or green. So remember, you need to subtract, so you need to do this formula, the non-mutually exclusive, whenever there's an opportunity for both of these things to be happening at the same time. So round and green is a possibility, so that's why we had to subtract those away, because otherwise they get counted twice when we do it from this perspective.